Okay, so here's the homework for 17. The key to this chapter, the number one thing you got to do is determine if you're doing a mean problem or a proportion problem. Before you start plugging numbers in, before you start writing stuff down, you got to figure out, am I looking at a mean problem or a proportion problem? If the question says average or mean, or they give you a standard deviation, you're dealing with a mean problem. So you have to use all the central limit theorem mechanics for means to do that. Like this one, they got a mu in there. Mu means population mean. This is a mean problem. They give me a standard deviation. This is a mean problem. Here, same thing. I see mu's, it's a mean problem. I see the word average, mean problem. No P hats, no Q hats, no success, no failure. That's a mean problem. Here, I haven't even read the whole question. I see the words standard deviation. That's a mean problem. Not going to have P's and Q's and P hats and Q hats, success, failure, none of that. I see the word mean problem. So most of these are mean problems. Here, this question, now we're talking about some percentage, some proportion of a group did something. That's a proportion problem. They don't say the word average in the question. They don't give you a standard deviation. This is a proportion problem. So now we're going to have P's and Q's and success and failure and all that. Same thing here. Look, 13% of some group did something. That's a proportion problem. Completely different from mean problems. You got to get those separated in your head. They're different universes, but they're in the same chapter, and it causes a lot of confusion. But most of these problems are mean problems. Here, 90%, 96% of the time, something did something. That's a proportion problem. Same here, proportions. Proportions. Means, they gave me a standard deviation. They give me a population mean. This is a mean problem. Okay, so let's do some more examples. So this is one of your homework problems, is number 11. I thought maybe we'd go through this one. So I'm basically going to do it for you here. Okay, first thing we got to do, especially on a written test, you got to identify your variables. This is a required step on those written assignments coming up. Required step. So I've determined already, I know this is a proportion problem. It's 13% of somebody did something. Well, of whom did what? We identify our population. Who are we talking about? Whom are we talking about? And what did they do? What are we calling success? So look, whatever comes after the word of is your population. Population is a group, not a number. A lot of times I'll say, what's the population? And the students will say 400. Population's a group, it's a category. My population here are the students. And what did 13% of them do? They were veterans. That's success. Now, the reason we write these two down is to help us write this next line. This next line is a required step. If you don't write this, I'm going to take points off. Let P, the population proportion of success, be the proportion of these guys that did that. Always. It's always proportion of these that did that. Of students that are veterans. Here in the next few days, some of you are going to be submitting your written assignments early, asking me to take a look at it. Or maybe after I've graded it, I take a point off of your chapter 17 written assessment. And I'll say, you didn't define your variable. And you're going to go, what? I don't know what you're talking about. This is what I'm talking about. Writing this sentence. That's what I call defining your variable. Let P be the proportion of your population that was successful. Okay, we're told we know what number that is. I think it was 13. 13%. We are told that 13% of students are veterans. That means Q, our failure rate, would be 1 minus P, or 87%. 87% of students failed at being veterans. Remember, success and failure don't mean good and bad. It means the thing you're studying either happened or didn't. We're studying whether people are veterans or not. Don't think good or bad. Okay, now we're supposed to check a bunch of conditions. So we have a sample. We have 289, and I want less than 27. In that sample. I gotta make some space here. Oh, evidently I made that thing small too. That was not my intention. Okay, so I want less than 27. So in my sample, I'm always going to have three things. Always. You're going to have an X, an N, and a P hat. And they're always going to give you two of the three. And you, this is going to be on your test. Identifying what all the letters stand for. If you don't know what the letters stand for, you're going to do awful on this test. Like, write all this down, memorize what these letters stand for. X is the number of successes in the sample. N is the sample size. P hat is the proportion of success in the sample. So my sample size was 289. I want 27 of those 289 to be veterans. I actually want that or less. P hat is always X over N. So 27 out of 289. Let me get my calculator. Okay, so 27 out of 289. That's 0.093. So that's much smaller than 13. That means my sample failure rate, 1 minus P hat. So I can do 1 minus last answer. Excuse me. Second answer, 0.907. So this is my sample statistics here. Now I want to check and make sure my sample meets the conditions of the central limit there. On a test, I don't need you to check all these conditions on on the midterm. Don't worry about checking the conditions. These questions are really boring if you don't meet the conditions. Like if this was a bad sample, we're done. Like I don't even continue. I would stop writing. If we determine this is a bad sample, we'd just be like, oh, we're done. I can't ask any follow-up questions. So unless a question specifically says check the conditions, I'm telling you, don't worry about checking the conditions because you know you're going to meet them. Otherwise, they can't ask a follow-up. Like here, the fact that they're asking me to actually give a numerical answer means I know I'm going to meet these conditions. But in the real world, we got to check the conditions. And we're supposed to check, is this a good sample? Obviously, if you, I don't know, we're someplace where you might have a lot of veterans. If you go to like, I don't know, an area that has a lot of veterans and collect your sample, you're taking a bad sample. That sample wouldn't look like the whole population. So none of your math would matter at all. So do we have a good sample? I hope. That's the best we can do. Let's say here, hope so. I didn't take the samples. I don't know, but I hope they did a good job. Are the samples independent? Does the act of going out and collecting this sample affect other samples? That's really hard to mess up. Samples are almost always going to be independent. What we really got to check is our size condition. We need n times p to be bigger than or equal to 10, and n times q bigger than or equal to 10. So n times p, what was p? 0.13. Is that question mark bigger than 10? .13. Yes. And then I need n times q. 289 times 0.87. That's bigger than 10. If this one's bigger than 10, that's a bigger number. Yes, we meet all the conditions. Hey, why do we care? What's that tell us? Oh, trying not to catch those up there. If you meet all the conditions, then here's our conclusion. I did it again. The central limit theorem will say, I'll just right here. Central limit theorem says that all possible samples of size 289, the p-hats, the sample success rates follow a normal distribution with the mean of that distribution is the population proportion of success, 0.13. That's what we had right there. And the standard deviation is square root of PQ over N. So we're going to have to calculate this. A lot of mistakes happen calculating this. You got to be really careful. Make sure, check this as I do it. Check it on your own calculator. Make sure you know how to use your calculator. I want the square root of P times Q, 0.13 times 0.87 divided by N, 289. And the whole thing, everything I type needs to be under that radical. Some calculators don't do that automatically, and you need to put parentheses around all this. So you might have to type this on your calculator, parenthesis 0.13, 0.89, 87 divided by 289, then close the parenthesis, then hit enter. Make sure you're getting that number that you see on my screen right there. So 0.098, I'll go several places. That wasn't right. 0.01. I guess if I'm going to go to this place, that's going to round up. So this is going to round to 0.02. Okay, so if a homework question asks you to describe the model, or if a test question says, give the model, we only know the name of one model. Anytime a question says, give the model, it's a normal model. That's the only model we know how to work with. The mean for a proportion problem, the mean is the population success rate, P, and the standard deviation is square root of PQ over N. So bad at this. There. I just need to make space. Okay, that's all set up. I haven't even begun to answer the actual question yet. That's all set up. Now I want to actually calculate what's the probability that somebody goes out and does a good sample of 289 and get less than 27. So what I really want here is the probability I'm writing here capital P for probability that X was less than or equal to 27. And you might be saying, well, the question said strictly less than. The normal model doesn't care the difference between less than and equal to, or just less than. Same thing. You're going to get the same answer. So this is the probability that my P hat is less than or equal to, what was my P hat? 0.093. So I want to be there and below. Draw a picture on these. Always draw your picture. This is a chapter 5 problem now. I've got this model here, a normal curve. These are all the possible P hats. I know right in the middle, the mean is P, this population success rate, 0.13. I want the probability of being right here. 9% is less than 13%. Or below. Drawing a picture is a required step. Pretty much everything you're seeing me right here, this is all required. You don't have to write, like this line here is not required, but everything else is. So it's a normal model problem. We find our z-score, the one I want, minus the one in the middle, divided by that standard deviation we just found. So we throw that in our calculator. Again, we always got to be careful with parentheses here. A lot of people type this in wrong. You've got to make sure that top is in parentheses. You want parentheses 0.093 minus 0.13 divided by 0.02. We get a negative z-score. Z-score is never your final answer unless the question, if the question says find a z-score, obviously you're done. But that's pretty rare. Z-score is usually not your final answer. What that says is this sample that they're talking about is 1.85 standard deviations below the mean. So it's not unheard of, but it's a little far below average. If we did an infinite number of samples on average, we would get 13% of the sample is a veteran. Okay, now that we got our Z-score, it's always the same. It's always draw the picture, find the Z-score, and normal CDF. So normal CDF. Smallest thing I shaded all the way down to negative infinity, which we write negative 99 to negative 1.85. Smallest things I shaded to the largest. Z-scores. These have to be Z-scores. Then we use that normal distribution button on the calculator. So second distribution, number 2. Make sure you leave these alone here. Don't change mu and sigma. Leave those alone. Unless you're very, very good and you know how to use the shortcuts, don't use them. Because I want to see the Z-score anyways. You're going to be finding the Z-score anyways. You might as well use it. Okay, my lowest was negative. No, not this. That's the minus button. Where's delete? Negative 99 to negative 1.85. And I get that answer, 0.032. That means, I'll type this one out. Let me make all this a little smaller again. I'm going to upload this document when I'm done. That's why I'm trying to make sure it's somewhat pretty and fits on the screen. So that number there, that's the probability of getting the sample we got or smaller because we went below. So this says the probability of doing a sample of 289 students and getting less than or equal to, again, that doesn't matter, less than 9.3% veterans is 3.2%. It's not impossible, but it's unlikely. It's unlikely if you take a good sample that you'll get that few veterans in your sample. So they asked this follow-up question. What do you think your results? Was that a weird result? If you took good samples and you just picked people at random, there's like a 3% chance that you would get a sample by chance that looks that weird, that far from typical. So we would say, yes, there's that's less, 3% is less than 5. There's less than a 5% chance of that happening. So what that might mean is, in the real world, we would look at that and go, well, something's probably wrong then. Because it's possible if you do 100 samples and they're all perfectly good samples, 3 times out of 100, you're going to get one that looks like this. So it happens, but it might mean that either maybe your sample wasn't good, maybe for some reason your sample was a biased sample and didn't have as many veterans as it should have because you did your sampling wrong. Or maybe it means that your original assumption, we started all this with that assumption. Maybe that number has changed now and we just didn't realize it. Okay, let's do another one. This is another proportion problem. We know that because first off, they're throwing percentages around. That's a pretty big hint. They don't say the words mean. They don't say the words average in the problem. Sure, in the question they do down here, but not here. They don't say the words mean or average. They don't give you a standard deviation. No, we got a proportion problem. 84% of somebody's doing something. So we start by defining our variable. What's our population? 84% of whom? Americans. What are they doing? What are we calling success? Own a smartphone. So then I like it when you write these two because that helps you write this next line. The next line's the one that's required. Let P be the proportion of these guys that did that. Required step. I'm going to keep saying this, and people are going to get mad at me on the Chapter 7 written assessment when I take a point off that they didn't do this. I don't understand. Like I've said it like 100 times. You got to define your variable. Okay, now they want us to describe the model. That means we got to go. We're supposed to check all the conditions. I'm going to skip checking the conditions. You know why? Because they're asking me to calculate a probability. I can't find a probability if I don't meet the conditions. So let's just assume we meet the conditions. Okay, so let's look at our sample. Oh, by the way, here we are told that P, the proportion of Americans that own a cell phone, is 84%. Our sample, we're always going to have an X, an N, and a P hat. They're always going to give me 2 of the 3 here. They're always going to give you N. Sometimes they give you P hat, sometimes they give you X. Here they gave me X. And then P hat is always X over N. 178 sampled out of 220 in the sample. That's how many smartphones, how many successes there were in the sample. That's how many people were in, how many Americans were in the sample. So 178 divided by 220. Let's call that 0.81. That's kind of far away from what we expected. We expect to get 84%. So just for clarity here, they gave me these 2 and I had to find this one. What if they give me these 2? So sometimes I'm just writing this to help you with other problems. You got to find X. And you do that. X is P hat times N. Use multiply to go up. Dividing going down, multiplying going up. Okay, we got to find our standard deviation. First, we need Q hat. That's always 1 minus P hat. So P hat is the sample proportion of success. Q hat is the sample proportion of failure. We know I'm saying the word sample because he's wearing a hat. That'll be 0.19. Then my standard deviation, square root of PQ over N. Oh, I need regular old Q. The population failure rate, 16%. 1 minus P. Over, what was N, 220. All right, so let's do that in our fits calculator here. 0.84 times 0.16 divided by 220. Check that on your own calculator. Make sure you get the same thing. I'm going to call that 0.025. Okay, now we haven't answered the question yet. Describe the distribution. Give the model. Look at all this stuff they want me to do. The model. Anytime somebody says the word model, you better say the word normal. We gotta give the mean, the standard deviation. Oh, it did say check the conditions. I forgot that I wrote that. In fact, I'm just going to take, I wrote this question. I'm going to take that out because I don't feel like checking the conditions right now. And we define the variable. Let P be the proportion of Americans that own a cell phone. What's our model then? Model is all P hats follow a normal curve or a normal distribution. With mean. Mu equals P equals 84%. That's an ugly 4. And standard deviation equals 0.025. There is describing the model. There is defining the variable. Okay, now we can look and see what's the probability of getting that sample. So we're always the same. It's a normal model problem. Draw a picture. Right in the middle, the average sample is P, 84%. That's, we literally just said that right there. My question, my sample here was 81%. And the question said, what's the probability of getting that or lower? Remember, you always have to shade something. It's always going to be or lower or higher, in between two. You're always going to shade something. Because we need 2 z-scores. And we find our z-score, the one I want, the one I care about, minus the one that's in the middle of the picture I just drew, divided by that standard deviation I just found. I'm lazy. I don't like typing the parentheses. So the way I type this out is I type out the top, I hit enter, then I divide by the bottom. Or you can do it all at once, but then you got to use parentheses on the top. Parentheses divided by 0.025. Sorry, that's a 2. Negative 1.2. Z-score is not your final answer. Then we do normal CDF. So let me write on here. Down here, Z equals negative infinity is way over here. That guy's Z-score right there was negative 1.2. That was right here. I can't type negative infinity on the calculator. I just type a big negative number. So I go second distribution, number 2. Remember, you never use number 1, ever. We want negative, I could type negative 100, negative 1,000, negative 1,000,000. I want a big negative number here. I always personally use negative 99 because it kind of looks like infinity. And then my second z-score, my biggest, was negative 1.2. Leave these two alone. 11.5%. So normal CDF of negative 99 to negative 2 was, I've already forgotten. 11.5%, 0.115. Okay, I've just run out of space there. This is still part of that. Word problems have word answers. The probability of doing a sample of 220 Americans and getting less than 81% have a cell phone or a smartphone, I guess specifically, is 11.5%. It's not very weird. Like, that could easily happen. It's not an unheard of like probability. Okay. I don't want to go through all these. All right, let's do this one a little quicker. Here, they didn't ask us to define the model. I don't have to go through the p-hats form a normal distribution. Well, I don't have to write that. I can, but I don't have to. I still have to define my variable, though. So 5% of people who open an email click on a link. This is real world, by the way. My wife and I just bought a business a few months ago, and I recently did a marketing campaign. I sent out a marketing email. These are real numbers. I looked them up as I was writing this, and I'm curious myself how good I did. Like, maybe my copy with the stuff I wrote was bad. I don't know. Let's take a look. So let P be the proportion of people who open an email that click the link. That's my population, people that actually open the email. Not everybody that got the email. The population is people that open an email. Success is they click the link. So we're told that's required. You have to write that. That's defining your variable. I looked this up. It actually said when I looked it up, the average is someplace between 2 and 5. Well, I don't know what to do with that if they don't give me an exact number. So I just kind of chose the higher number, 5%. So let's pretend this is true. That when people send out a mass email, of the people that actually open the email, 5% of them actually click on something and go to some external website. That means the population failure rate is 95%. Here's my sample, like literally, this is my sample. We have an X, an N, and a P hat. 38 successes in the sample. 38 people clicked on a link. I sent out like 3,500, 1063 opened the email. So my success rate for my sample was 38. It's not typing. Out of 1063. Let's call that 0.0357. I'm going to run out of space here. I got to make this smaller. I never give myself enough space on these problems, or I write too big. Okay, so my standard deviation, square root PQ over N. A lot of mistakes happen here. People want to use these numbers. Use the population numbers. 0.05 times 0.95 over what was in 1063. This is going to be kind of a small standard deviation. 0.007, let's call it. Okay, then I'm not going to write it out, but I guess I kind of drawn the picture of it. All possible samples of size 1063 will have success rates that follow a normal distribution. And the average sample, excuse me, would have a success rate, same as the population, of 5%. Standard deviation, 0.007. I want to find the probability of getting the sample I got. I want to figure out, was mine a weird sample result? Now, you can't calculate that probability exactly. There are ways to do that. It's called using the binomial distribution. But with a normal model, you got to shade something. So I'm going to have to find this probability. If they don't tell you what to shade, you always shade a tail. So my z-score is the one I want. In all the examples we've done today, we've gotten a negative z-score, and that's just because the problems I picked happen to work out like that. You could easily have a picture that looks like this, where you've got some p hat here and you're shading above. That will happen just as often. All right, so I'll use the parentheses this time. 3, 5, 7. The one I want minus the one in the middle of the picture I drew, divided by the standard deviation I just found, negative 2.04. And then normal CDF, smallest thing you shaded to the biggest, and these are both z-scores. So negative 99, negative 2.04. 2%. Let's just call that 2%. So what this says is, if you go out and do millions and millions of samples of size 1063, 2% of those samples will have click-through rates less than what I got, 3.57%. So what's that suggest about the sample? That's 2% is a small number. That means there's probably something wrong with the sample. That means we probably weren't allowed to do this. We probably didn't meet the conditions of the central limit theorem. Central limit theorem says you should have a good sample. There's probably something wrong with my sample. So this is a small, very, very small probability. There may be something wrong with the sample. So I keep saying, don't stress about checking the conditions of the central limit theorem, because you don't know if you've got a good sample a lot of times until you do the math, and then you look at your probability and you're like, oh, okay, maybe I didn't have a good sample. So you got to do the math first to get a hint at that. And this tells me that there's probably something wrong with my sample. Either maybe the people that I sent this out to are just less likely to click on ads. That's one possibility. That my email list isn't very good. It doesn't represent the population. Or maybe it means that the email I sent out wasn't very good, which is probably the most likely. Because like, I don't know what I'm doing yet. I'm not in marketing. Okay, now let's do some mean problems. I don't think we're going to have time to do these today because I got another class, but I've got a couple of mean problems worked up. I will do these next time. maybe, what have I got? Just one here? Yeah, I guess I could do one. Okay, here's a mean problem. I know it's a mean. Oh, I didn't give a standard deviation. I don't know. This is real world data again from my shop. I just realized I didn't give a standard deviation. Maybe we can get this done real quick, but I'm gonna have to make up numbers here. Let's say 75 cents. That's probably more than that. Let's say $1.20. Okay, so it's a mean problem. They tell me a population average. They tell me a population standard deviation. It's a mean problem. No successes, no failures, no P's, no Q's. This is all mu's and sigmas. First thing we got to do is define our variable. So what is it we're talking about here? The average amount spent at our store. Like, again, I looked this number up today for the last, it doesn't tell me a time frame. But our recent average is $27.94 per transaction. So let mu, the population mean, be the mean amount spent and we're told that that's $27.94. That's defining my variable, required step. Notice it's mu, not P's and Q's. We're also told sigma, the population standard deviation, is $1.20. Okay, now I'm supposed to check all the conditions. I'm not going to really because I'm running out of time here. I've got a sample. In the sample, they give me an X bar, a sample mean of 30. This says the next customer. This is n equals 1. N equals 1, we can't do. I don't know the distribution of all customers. I'm not told that the population is normal. I can't make predictions about the next person because I don't know what I don't have a button on my calculator that says customers at Steve's store. It's not a normal distribution, or they would have told me that. N is too small. If your population is not normal, your sample needs to be big. That's too small. I can't answer this. If the question said normal distribution, if it said the population is normal, then this would be a chapter 5 problem. We can make predictions about any size sample, even 1. Same thing here. 4 customers, still too small. N is too small. The general guideline is if you know the population is nearly normal, small samples are okay. If it's really close to a normal distribution, maybe you could get by with a sample size of 4. If it's not, your sample needs to be at least 50 is the guideline I was always told. So now, okay, here we go. So now N is 60. That's bigger than 50. It's probably okay. And we're told a sample mean of $30. And in fact, we want the probability, capital P, that X bar is bigger than or equal to 30. Okay, so I draw my picture. Right in the middle is the population mean, 2794. I want bigger than 30, so here's my X bar, my sample mean of 30. And I want to be above that because the question said above that. I drew my picture. I find my z-score, the one I want, minus the mean, the one in the middle of the picture, divided by Oh, I got to calculate the standard deviation. Here's where mistakes happen. Can't use that. This standard deviation for this model is sigma divided by square root of n. So $1.20 divided by square root of 60. .15. That's the standard deviation that goes here. That's going to be a really big z-score. Divided by 0.15, 13.7. That's a gigantic z-score. Z-score is not your final answer, though. Now I do normal CDF. Smallest z-score I shaded up to the largest. How far did I shade? I shaded all the way up to positive infinity. So 13.7 to 99. Hit paste. That is not 5%. You got to be careful on these. You can't have a probability bigger than 1. That's 5.29 times 10 to the negative 43rd power. That's literally almost impossible. That's an incredibly small probability. So I'm not talking about individuals. We can't even make predictions about individuals here because we don't know what the population looks like. We can make predictions about samples, though, as long as our samples are big enough. So I'm saying that what's the probability the next 60 people that come in spend an average more than 30? When the typical person only spends 27, it's pretty unlikely that 60 people in a row on average are going to spend more than 30 each on average. Okay, that's a good place to stop. I'll upload this document in the announcement when I post this recording. Stop.